Hello, my name is Jaina, and I will be going over the topic of binary search. But before we dive into that, let me tell you a little bit more about data structures. Data structure is the most important and fundamental building block concept in computer science, and good knowledge of data structures is a must to design and develop efficient software systems. So let's get started. What is a data structure actually? A data structure is a way to store and organize data in a computer so that the data can be used efficiently. But in this video, we'll particularly focus on the most famous and fundamental algorithms in computer science, which is the binary search. We find the applications of binary search in a large number of problems in computer science. But here, I will try to present it in the most simplest form, and to do so, let me first define what is binary search. Binary search is also known as half-interval search, an algorithm used in computer science to locate a specified value within an array. For the search to be binary, the array must be sorted in either ascending or descending order. Let me define a problem first to help you better understand what it is. A problem is given such that a sorted array of integers. A sorted means that the elements in the array are arranged in either increasing order, like in this array here, or the elements are arranged in increasing order. Let's say the name of this array is A. The size of this array is 9, so we have index starting 0 till 8. Now, given such an array and a number or an integer x, we want to find out whether x exists in this array or not. And if exists in this array, then we want to find out the position at which x exists in this array. So, for example, if x is 81, does it even exist in the array? Yes, it exists in the array and it exists at index 7. Does 25 exist in this array? No, 25 does not exist in this array. Does 21 exist in this array? Yes, 21 does exist in this array at position 3 and at index 3. Now, what would be the logic to find out whether x exists in this array or not? One simplest approach can be that we can scan the whole array to find out the desired number, so we can start at index 0 and compare this element with x. If it is equal to x, then we are done with our search. We have found the element in the array. If not, we go to the next element and we keep on comparing with the next element until either we are finished with the array or we find the number. So let's say if you wanted to find 63 in this array, then the search would be over when we reach at index 6. We start at index 0 and a search would be over at index 6 if you wanted to find out 25. Our search would be over at index 8 with the conclusion that 25 does not exist in this array. This approach will work irrespective of whether the array is sorted or not, and if I have to write the code for this, it will be pretty straightforward. Let's say I want to write a method search that takes an array A, its size n, and number x we search for, and the code would be and will be running a loop starting 0 till n minus 1. So for I starting at 0 to n minus 1, if the elements at index I is equal to x, then we return I, which means returning the position at which we have found the element x. And the search will be over, and if we cannot find any such I, then we return minus 1. Let's say returning minus 1 means that we could not find the elements x in the array, and now with this algorithm, if we are lucky enough, we will find x at first position itself. So in the best case, we will make one comparison and we will be able to find out the result in the first case when x would not even be present in the array. We will scan the whole array and we will make n comparisons with all the elements in the array, and then we will be able to give back a result that hey, x does not exist in this array. So the time taken in the worst case is definitely proportional to the input size of the array. Size of the array, or in other words, we say that it would be big O of n in terms of time complexity. It's always good to analyze the running time of an algorithm in the worst case and find out the upper bound of time taken. Now in this case, the time taken grows as a linear function of n. So we also call this search linear search. And once again, if we are using linear search, we are not using any property like the array sorted or not. Whether that is sorted or not, this will still work. Now let us try to improve this algorithm using the extra property of the array that is sorted. Let us say we want to find out whether 13 number exists in the array A. So x is 13 and we want to find out whether x exists in this array A. Now we will use a different approach this time. Instead of comparing x with the first element as we do in the last case of linear search, we will compare it with the middle element in the array. Now the size of this array is 9, so the middle element will be at index 4. Now there will be three cases here. Case 1 can be that x is equal to the middle element If x is equal to the middle element, we have already found x in the array. Case 2 can be when x is less than the middle element, and case 3 can be that the x is greater than the middle element. Clearly, if x is equal to the middle element, our search is over because we already found the x. If x is equal to the middle element, our search is over because we've already found the x in the array. So if x is less than the middle element, then because the array is sorted, it lies before the middle element, and we can discard the middle element and all the elements after the middle element. Similarly, if x is greater than the middle element, it lies after the middle element. So we can discard all the elements before the middle element and of course the middle element as well. So in case 2 and 3, we discard half the elements from a search space and reduce our search space. Initially, our search space is the whole array. X can exist anywhere in this array. Now we compared with the middle element, which is 36. Now x is less than 36, so it should exist somewhere before 36. So we discard all the elements after 36 and 36 as well. Now the problem gets redefined. We need to search x only between index 0 to 3. So how do we keep track of the search space? We keep track of the search space using two indices, start and end. So initially the start would be 0 and end would be the last element in the array, in this case the right index 8, because initially the whole array is our search space. We'll calculate mid as start plus end upon 2. Now, once we find out our reduced search space, we adjust start and end accordingly. So in this case, after comparing 13 with 36 and discarding half of the array, our end now becomes index 3, which is nothing but 1 less than the middle element. Now we will again find out the middle element in this reduced search space. So here the middle element will be 3 plus 0 by 2. If we take only the integral part, 3 plus 0 by 2, it would be 1.5. And if we take the integral part, the middle element would be index 1. Once again, is it equal to x? No, 6 is not equal to 13. Is x less than the middle element? Is it case 2? No, it is not x. No, it is not. X is greater than the middle element. So this time we discard the middle element and all the elements towards its left. And this time we shift start to mark a new search space now. The new search space is starting at index 2 and ending at index 3. Now what if the middle element 3 plus 2 is 5? So 5 by 2 is 2.5 and the integral part is 2. So this is our middle element. So x is now equal to the middle element. We have found our element, so we are done with our search. This kind of search, where we reduce the search space into half at each comparison, is called binary search. Once again, we are able to reduce the search space by 2. Or in other words, we are able to reduce the search space into half only because the array is sorted array. Being sorted is a precondition for binary search and it is essential. Okay, so let us now go through the code for this algorithm. I have written a method binary search that will take as an argument an array A, its size n and A, number x to be searched for this array, and I will initialize two variables, start to 0 and end to -1. So start and end define a search space. Initially the whole array is our search space. Now I have written a condition here, while start is less than or equal to n. And I'll come back to why I have written this condition. So while this is true, start is less than or equal to n. We will find out the middle index of the search as start plus n upon 2, and now we will write three cases. If the middle element is equal to x, then a search is over. We return the index stored in the variable mid and exit from the function. If x is less than the middle element, then we need to discard all the elements having index greater than or equal to mid. So our end of the search space now becomes mid -1. And in the third condition, which will be x greater than the middle element, which will be the default condition after these two, if and else, if we need to discard all the elements with index less than or equal to mid, so our start becomes mid +1. And if we exit this while loop without returning anything, then we return -1, which will mean that we were not able to find the element x in this array. Now, why this while statement here with a condition start less than or equal to the start and the end pointer? Now there must be an exit condition to our recursion. The exit condition can be either we find the element in the array, so we return and exit, or we exhaust the whole search space when start is equal to end, or start is less than end when we still have search space. When start is equal to end, then our search space has only one element. So when this condition becomes false, we have exhausted our search space. We need to exit the loop and we need to return -1 to tell that the element the number x does not exist in this array. Now once again, in this case, which is in the best case, we can find the element x in just one comparison, when the middle element itself will be the element x. In the worst case, we will keep reducing the search space until the search space becomes one element. So from n, we reduce to n by 2, and from n by 2, we reduce to n by 4, and we go on till our search space becomes 1. Now, how many steps does it take? Let's do some maths here. Let's say it takes k steps to reduce n to 1. By dividing by 2 at each step, so n by 2 upon k will be equal to 1. If you solve this, then k will be equal to log of n, then the base will be 2. So in the worst case, binary search will take log n comparisons, and so the time taken also in the worst case is proportional to log in, or in other words, it is big O of log in terms of time complexity, and big O of log n is a lot more efficient than O n algorithm. So this was my second presentation for CS490 on binary search, and this concludes the end of the video. Thank you.